Welcome everyone to the Ultrasound Physics and Math series. My name is Dia Al-Khatib. I'm one of the cardiology fellows at the UT and currently the academic chief fellow. I will be giving a few lectures to explain some of the concepts of ultrasound physics and math. Recently, I had my echo boards, and there's a lot of concepts and questions we are being asked in the exam. A lot of them are simple and they rely on the simple concept. So what I am going to do through this series, I'm going to use Edelman physics chapter heavily, and we're going to go through each section and discuss in details and simplify those parts so we can emphasize on the concepts. Today, our talk will be focused on the introduction of the ultrasound by defining the ultrasound itself and talking about some of the ways we describe the ultrasound. So before we start, the way we think about it is there are two types of waves. So main types are mechanical wave, and the other type is electromagnetic. Our focus will be on the mechanical wave, and the way I think about it is electromagnetic is a type of energy that does not require any medium, and it can move through a vacuum. So I'm going to mention that here. Through space or vacuum. Whereas mechanical wave, the way it is described is basically it's a type of wave that carries energy from a point A to point B. So this is point A, and this is point B. And in order to move the energy from point A to point B, what happens in sound wave, which is a type of mechanical wave, there will be some vibration of an object. And this vibration causes this object, which is say the sound wave, to move from point A to point B. Now, the way this vibration affects this object to move from point A to point B will result in some areas of high, let's say, pressure or density. They are known as compression. So if you think about it, let's say this is the area with high pressure, and then it kind of gets a lower pressure or lower density, and then again higher pressure, and then followed by low pressure or low density. These areas of high pressure, they are called compression. As you see here with the blue, and these areas in green, they are called rarefaction. So the difference between the compression and rarefaction, as we see here, is areas of compression, they have high pressure or high density, whereas areas with rarefaction, they are far from each other, so they have a lower pressure or lower density. So that is a best way to describe the sound wave. As we said, it's a mechanical wave. It moves some object from point A to point B by vibration that will result in areas of high pressure or density known as compression, followed by areas of low pressure or density known as rarefaction, and that's how the sound wave forms. Now, as we see here in this chapter, we describe the sound as a type of mechanical type of energy, and that means it will move an object, as we said, from point A to point B through vibration, and this vibration would result in areas of compressions and areas of rarefaction, as we explained there. Now, part of the definition of the mechanical wave, as we said here, it does not move or transmit in space, so that's very important. So you have to have E medium. Now that's the first way to describe the sound wave. The second way we describe the sound wave is there are two different ways of movement of these objects. The first one is what we call transverse, and the second one is longitudinal. The way it's best explained, let's make here a graph. So if this is the baseline or the direction of the wave, this is the direction from point A to point B. When the ultrasound or the sound or the wave, whatever type, causes these objects to move in a direction that is kind of perpendicular, as you can see here. So it's almost going to the right and left, so it's almost perpendicular to the direction of the wave itself. This is what we call transverse. Whereas sound wave, for instance, is characterized by what we call it longitudinal. So the moving objects would be in the same direction. So this is compression, as we said before, rarefaction, compression, rarefaction, as you can see here. So the direction of these objects or the vibration is happening in the same direction as the overall direction of the sound wave itself. And this is what we call longitudinal wave. Okay, I hope that's very clear. So we can see here in the Edelman's chapter describing that in transverse type of wave, this particle move in the direction is perpendicular at a right angle to the direction of the wave itself. Whereas in longitudinal, these particles move in the same direction as the wave. Now, that is the definition of sound. So it's mechanical and it's longitudinal wave, meaning in straight line. Okay, now, before we describe the wave itself, just to know what is ultrasound itself mean. And it's gonna come shortly, but I think it's very important to be on the same page. So the word sound itself describes, we can mention in here, that sound is characterized by a frequency. We're going to talk about what is frequency, characterized by frequency between 20 to 20,000 cycles per second or hertz. When we say ultrasound, the word ultrasound means above, so anything above 20,000 cycles per second or hertz. And the word infrasound is anything less than 20 cycles per second or hertz. So that is the basic definition of ultrasound. Anything we describe sound wave applies to infra and ultrasound. So since we said sound wave is a type of mechanical energy, and it's type of mechanical wave, and it's longitudinal, so ultrasound would be the same. It's going to be mechanical longitudinal wave. Now, as we said before, in order to form a sound wave, we have to cause some vibration of these objects, as we see here. So you vibrate them and you cause movement from point A to point B. The way we describe these areas, as we said, compression are characterized by high pressure, high density, and then rarefaction, low pressure, low density. This pressure or density, or something called distance, how much these particles are able to move from point A to point B, are known as acoustic variables. So the variables in particular, they identify the sound wave, meaning that without these variables, there is no sound per se. Meaning, if this wave here, as we can point out, as you can imagine, this is the compression, high pressure, high density, followed by rarefaction, low pressure, low density. If there was no variation, if it was the same pressure, same density, no movement, no vibration, then there is no sound wave per se. It's just an object that is not moving. So in order to form the sound wave, you have to have some variation in these variables that will identify the sound wave. Now, pressure is defined as an area, as a force within an area. So how much you apply force within that area, and the unit is pascals. Density, as we know, is a mass within a volume. Kilos per meter squared, kilos per centimeter, to the power 3, because we're talking about volume. So again, mass within a volume, so it's kilos per centimeter to the power of 3 or meters. Now, distance is what we call particle motion. So what that means, as we said, you have point A, and then these particles are being vibrated to move to point B. So this motion of these particles over time will result in some distance. So that is the particle motion. So that's for the acoustic variables. Now, to describe the sound wave itself, there's 7 parameters. They are very important. They are related to each other. Our discussion here today will describe the relationship between each other. Some of them are directly or inversely related to each other. Some of them are the factor that characterizes the ultrasound itself, meaning that we cannot change them, and some of them are being changed by the sonographer through the machine. So we're going to describe that in our discussion. To start with the period and frequency, first, let's imagine what is the ultrasound wave looks like. So some basic concept. Okay, so let's imagine this is the y-axis, which is the time here. And let's say this is the time. And here, this is 1 second, this is 2 seconds, this is the beginning. So now, the first thing we need to identify of any sound or ultrasound, there's something called cycle. That is 1 cycle here, as we can see. It's from the beginning to the end of that cycle. That is 1 cycle. Now, this continues. That's another cycle from the beginning here to the end of it. So that's another cycle. And then another cycle, let's say, goes up, and the same thing. Now, the duration of each cycle is called period. It's measured in time. So it's the time required to complete a single cycle. This period in ultrasound wave is described usually in microseconds, since the ultrasound we use will have a very high frequency, since the name ultrasound. So the period will be very short, and I'm going to explain that in a few seconds. So to define the frequency, which we will bring it back with the period, frequency is the number of cycles in 1 second. So if I tell you over this example here, if this is the y, I'm highlighting it, the y-axis, which is the time, and I tell you that this is 1 second. The whole period of time is 1 second, let's say. So how many cycles in that 1 second? 1 second is defined as frequency. So that's the first cycle, second cycle, third, fourth, fifth. So there are 5 cycles within 1 second. So the unit of cycle per second is also known as hertz, and that's the shortcut. So if we say what's the frequency here, it will be 5 cycles per second, or 5 hertz. Now, what is the duration of each cycle? So here we said there were 5 cycles in 1 second. So the duration of that cycle, known as period, would be 1 divided by 5, which would be 0.2 seconds. So if you notice that the frequency and period are related somehow to each other, and the relationship is an inverse relationship. Let's imagine here, if we said that we had 5 cycles in 1 second, that was associated with a period of 0.2. So if we use the same time, which is, let's say, 1 second, but this time, instead of having 5 cycles, we're going to have 2 cycles with the first cycle, second cycle. So what's the frequency here? So frequency will be 2 cycles per second. which will be 2 Hertz. Now, what's the period? Period is the duration of each cycle. So we said 2 cycles in 1 second. The period will be 0.5 seconds. So as you notice here, when we decrease the frequency, decrease the number of cycles, that cycle will take a longer time to finish, so the period increase. And this brings us to the first equation we need all to memorize, which is frequency times period equals 1. That brings us to the relationship, which is frequency is inversely related to period. Now, for maths, for application of that equation, the frequency time period equals 1, we have to use the same unit, meaning that if we use the Hertz, which is 1 per second, we have to use period in seconds. If we use something called megahertz, which is defined as 1 divided by second to the power of 10 minus 6, which is basically 1 million, then we will have the period in microseconds. And that's very important. The question might give you, let's say, an example of a frequency, say, of 10 Hertz. So then the question is, what's the period? So you apply the equation, period times frequency equals 1, then 10 times period equals 1, then period equals 1 divided by 10. What's the unit? We use Hertz, so we're going to use seconds. So the period will be 0.1 seconds. If the question gives you the same frequency equals 10 megahertz, so there are 10 millions per second, then period will be 1 divided by 10. Since the unit is megahertz, the period will be, or the time will be in microseconds, so it will be 0.1 microseconds. And that makes sense. If you think about it, there are 10 million cycles in 1 second, then the period is very, very short, 0.1 microseconds. So that's the first thing. If you notice this equation, frequency times period equals 1, they are inversely related to each other. There's no other factors contributing to this equation. And that's why frequency and period, both of them are determined by the sound source itself, meaning that the sonographer cannot change the frequency or the period. Okay, and clinically, all of us know if we have to change the frequency, we need to change the probe. Why is that? Because frequency is a characteristic of the sound itself, the probe. We cannot just increase the frequency using the same probe. Some probes, they say they have 2 megahertz, some of them have 8, some of them have 5, and that's how we change frequencies. So that's the first concept. Okay, now in real world, as we said before, by definition, anytime we say ultrasound, anything above the sound, which is between 20 and 20,000, then ultrasound will be anything above 20. In real world, machines typically use ultrasound frequency ranging between 2 to 10 megahertz. Okay, so 2 to 10 million hertz, much higher than just like the ultrasound that is by definition, ultrasound is above 20,000. So usually we use more than 2 to 10 million hertz. That's the ultrasound we use in cardiology. Now, we finished the frequency and period. We mentioned that we have to use, again, this is very important, the same unit. So if we use cycle per second, we use the period in second. If we use kilohertz, it's going to be milliseconds. If we use megahertz, and I'm going to mention it here, we're going to use microseconds. So microseconds correlates with megahertz. And typically the exam will ask either this one or this one. So if it gives you megahertz, you're going to measure or calculate the period in microseconds. So we finished the first 2 characters of the ultrasound. We go back here. and we look at them. So we have period and frequency, and these two again are determined by the sound itself and cannot be changed by the sonographer. Now the next three are related somehow to each other, and we're going to describe them, something called the amplitude, power, and intensity. So for the amplitude, the way we describe it, if you think about it, this is the baseline of that variable, as we said before, and how much this variable goes above and below the baseline defines the amplitude. And if you notice, we mentioned here the variable, and we said before, variables can be pressure, can be density, and what so. So here, if the wave has a higher pressure, it will go up, and when it has a lower pressure, it will be down. The amplitude is defined as how far the wave can go from the baseline. So if you notice, typically the cycle has it goes above and the baseline, above and below the baseline equally. Hence, the amplitude is how far that wave can be from the baseline. So the distance between how far it can be from this baseline, this defines the amplitude. There's something called peak to peak. Amplitude is the total deviation from the top to the bottom. So it will be 2 times the amplitude. Okay, so I'm going to write that equation here. Peak to peak. Amplitude A, let's say, equals 2 times amplitude, because it has the distance above and below the baseline, and that's why it's 2 times amplitude. Question will ask you about the amplitude. So peak to peak, we don't really use it clinically. Now, so the difference between this average value and the maximum value of that variable is the amplitude. Now, amplitude itself can describe pressure, can describe density, can describe particle motion. So if it describes pressure, the difference between them will be in Pascal. If it describes density, will be the unit of density, which is grams per cubic centimeter. And if it describes particle motion, will be a unit of distance. Now, to make it easier clinically, the agreement was to use a description called decibel, which is the way we describe amplitude, which is technically a unitless. It's not a real unit, because if you notice the amplitude, it describes how far you deviate from the baseline. So there is no real actual unit, and that's why clinically and for our echo and ultrasound, boards purposes, we will say amplitude is expressed in decibel. And the abbreviation for it will be this way. That's how we describe it. Now, the amplitude and whatever comes with the amplitude, we're going to talk about it, initially is determined by the sound source, but the sonographer can change it, can increase the amount of vibration of that sound or decrease it, or the pressure or the density of that sound wave. That will be the way we change the amplitude. So it's very important to know that sonographer can indeed change amplitude. Okay, now this sentence here, will come back to it later, but I think it's simple to kind of imagine that what happens with the ultrasound wave when it passes through some tissue. Let's say this is the baseline here, and let's say this is the body here. So the ultrasound starts with a high amplitude, let's say this way. Now it's going through some tissue here. This is like the body tissue. So the body tissue kind of will resist that ultrasound wave. So the ultrasound will become less or become weaker. And again, we express that through amplitude. So the ultrasound would say amplitude was, let's say 5 decibel before. Now, when it goes through the tissue, it's going to be a little bit lower. So it goes to 4, let's say, and then lower, 3, and then lower, 2, and then even lower, 1, and what so, and it keeps going. So that is something called attenuation, that the amplitude of the ultrasound wave decreases over time when we pass through the body. Okay, so that is the amplitude. So if we say, if we use the same wave, 5 decibel, let's say, and it passes through 2 centimeter of fat versus 5 centimeter of fat, 5 centimeter of fat tissue will cause more attenuation. The ultrasound wave will decrease more, and that's why amplitude itself will decrease as the ultrasound wave propagates or passes through the body. The more it passes through the body, i.e. the deeper, it will be more likely to be attenuated or will be weakened, or the amplitude will go down. So that's very important, and we'll come back to it. This is very important when we come how we adjust our image quality. Now, the fourth way we describe ultrasound, something called power. And the power is the rate at which energy is being transmitted. So we know the unit of watts, which is how much we are, or how fast, or the rate of that energy being transmitted, meaning higher watts or higher power, that is more work is being transformed or transferred in that period of time. So that is what we call it watts. And very important concept. And this is kind of like a little bit like a formula, or more like a relationship. Power, we need to memorize, power is directly related to amplitude square. So the amplitude of that sound wave we mentioned before, if it goes up, the power will go up. Now, what's the relationship? So the question might say, the first wave amplitude was, let's say A1 was 5 decibels. Now, if you increase that, if you double it, you make it 10 decibel, what's going to happen to the power? We apply that equation. So here the amplitude is twice. So you'll be 2 times, and then since the power is related to amplitude squared, then 2 times 2 equals 4. So here the power will go up 4 times. What about if the amplitude went from 10 or from 5 to, let's say, 15? So 15 is 3 times, so the initial amplitude, so then 3 times 2, that will be 9, then the power will be 9 times higher. Now, the same thing applies, since the amplitude can be changed by the sonographer and the power is related to the amplitude, then sonographer can change the power. Now, as we know, even from real life, higher power, higher danger, because you are transferring higher energy over a period of time that might cause some body damage. So when we talk about this power and the next one, the intensity, we always need to consider the safety. Yes, ultrasound is much safer than other imaging modalities, but there's still some energy being transferred. Now, we move now to the intensity, which is one of the variables of or one of the parameters that we describe ultrasound wave. So intensity is defined as the concentration of energy in that sound beam, meaning that if we give that power over a surface, then in that surface per se, how much power we give. So basically, intensity as an equation, and we can use the intensity equals power divided by area. So if you increase the power, you will increase the intensity because you're applying more energy in that area. Now we go back, again, power is directly related to amplitude squared. So if you increase the amplitude 1 time, but you double it, then the power will quadruple. If you increase the amplitude, also that will increase the intensity, and it's the same relationship. If you think about it this way, is since intensity equals power divided by area, then you can apply that. Then intensity equals amplitude squared divided by area. Let's say the area is fixed. So if you increase the amplitude, then this will increase the intensity. And again, it will increase by the same way. So if we increase the amplitude 3 times, then the intensity will increase 9 times. Okay, since amplitude is a factor that we can change, the sonographer can change, then the power and the intensity can be changed by the sonographer. What's the unit of the intensity? Is power, which is watt, divided by area. It can be square centimeter or squared meter. Okay, again, we go back. If we apply more power to that area, we are causing more damage. And that's why intensity is a key parameter for safety and bioeffects. We're going to talk about it later when we come to biology, how we improve the image quality. If the question gives you options to improve the image quality, and there's an option by increasing the power or the intensity, that will cause more harm. So you'll always avoid increasing intensity or power as possible. We will try to decrease the power intensity because that's a key for bioeffects and safety. Now, the last two parameters we're going to describe here are the wavelength. So before we mentioned that when we were talking about the ultrasound, how we describe the frequency and the period over the y-axis, which was the time. But here the y-axis will be distance. So here we talk about distance, and this distance can be in centimeter, can be in meter, can be in micrometer, and what so. So that's very important. The question is, how long is that cycle? So this is one cycle. How long does it, and when I say how long, I mean distance. That is the wavelength. So the length of each cycle over the y-axis, which is the distance, is defined as the wavelength, as we see here. Now, the same concept, so let's apply here, and we can say, if I tell you here that the y-axis here, the distance, let's say this is 1 centimeter here over this, and here the same thing. So here we have 1, 2, 3, 4, 5. We have 5 cycles in that 1 centimeter, whereas here we have on the right, we have 1, 2, 3 cycles in 1 centimeter. So you can tell that on the left with the 5 cycles, they are shorter cycles. The wavelength is shorter compared to the one on the right. Now, the formula that all of us need to know, and that's very important, we're going to connect it with the 7th parameter, which is the speed, that the propagation speed, which is the rate at which ultrasound or sound wave travels through a medium. We know that sound wave is a mechanical wave, so it needs a medium. So that medium will determine the speed, meaning that some medium, we're going to talk about that in a second, some media has a tendency to have a higher speed versus other medium will have a lower propagation speed. So the formula that we need to remember is speed equals frequency times the wavelength. And for abbreviations, speed is known as C equals frequency times wavelength. Now, the speed will be a unit of time over distance. So if we use the speed of meter per second, okay, we're going to use frequency in hertz, which is 1 per second, times the wavelength will be in meter. That's very important. The same thing applies. If we use speed in millimeter per microsecond, then we're going to use frequency in megahertz, and wavelength will be in millimeter. Okay, now each medium, as we said before, it has its own propagation speed, and we're going to remember these numbers. But before we go, so the medium itself has kind of different features, and that will determine the speed itself. There is something called stiffness, how stiff is the medium, and then the density. So think about it this way: if the medium has a higher density, it's more dense, there's more mass in that volume, that will resist the sound wave, and that will decrease the propagation speed. So the first concept that we connected together, we say speed is inversely related to density, and that makes sense. Now, the second thing is the stiffness. Stiffness is different from density. This is very important, that stiffness is completely different from density. Density is mass within volume, higher density, again, more mass in that volume, so it will resist the sound wave. Whereas stiffness is kind of like, it's solid, it's stiff, that will enable the ultrasound or the sound wave to propagate. And the way we remember it, and I think Edelman mentions that, mnemonic is stiffness, okay, is the same with speed. So you can like think about it, S is as the same as speed. So meaning that speed is directly related to stiffness. So that applies here, that air, for instance, is much less stiff than soft tissue, and that's why the propagation speed of the air is much lower. For exam purposes, all of us have to remember the speed of soft tissue, blood, body tissue. Usually rely on the fact that they're kind of similar, and they're soft tissue. The speed is 1540 meters per second. Now, I would like you to also remember that if we use the other unit, which we mentioned here before, the millimeter per microsecond, it's going to be 1.54 millimeter per microsecond. So the question might give you a frequency in megahertz and ask you to calculate the wavelength. So if the question gives you the frequency in hertz, then you can use the speed in meter per second. You don't need to convert. That way it's much easier for you. If the question gives frequency in megahertz, then you can use directly the speed, which is 1.54 millimeter per microsecond. We're going to use some examples soon. But we go back here, since let's think about it this way. The medium itself determines the frequency, okay? Now, I'm sorry. The medium itself determines the speed, okay? And we mentioned before that the ultrasound probe itself determines the frequency. Then the wavelength is affected by the medium through the propagation speed and through the ultrasound source itself through frequency. And that's very important, meaning that human factor cannot change wavelength. We as sonographer cannot change the wavelength. And again, the explanation goes back to that equation here, that the medium determines the propagation speed, the ultrasound probe itself determines the frequency. Then since it's an equation, so that means the wavelength is directly related to the propagation speed, inversely related to the frequency. Now, we mentioned that, and we discussed the rule of density, speed, stiffness, and speed, and how that affects the propagation speed. By the way, for accuracy, I hear sometimes people to say velocity. The difference between velocity and speed is when there's no direction, when we don't mention any direction, we don't say velocity. We're going to come later to Doppler shift and Doppler equation. We mention the direction, we measure the angle, then that time we use velocity. Whereas when we don't describe the direction of the flow or the moving object or these particles when they vibrate, we just say speed. Now, to summarize things back together here, about period and frequency. So we go back to the equation. I'm going to mention them here, that frequency times period equals 1. So they are inversely related to each other. And again, remember, use the same unit. So if you use frequency, which is cycle per second or hertz, you're going to use period in seconds. If you use frequency in megahertz, then period in microsecond. Again, they are inversely related to each other, and they can be changed by changing the sound source, the probe. Sonographer cannot change period or frequency. Now, the other three parameters we mentioned are amplitude, we describe it in decibel, power, and intensity. And the equation that we need to remember is power is directly related to the amplitude square, and that's very important. I'm going to highlight it here. If you double the amplitude, then the power will quadruple. And then we mentioned the intensity equals power divided by area, which equals amplitude squared divided by area, because area is fixed. So if you increase the amplitude, then the intensity will increase, will double, as we mentioned. And again, these factors or variables can be changed by the sonographer. So they are adjustable, and that's the word here. They are directly related to each other, and they are adjustable by the sonographer. We increase the amplitude, we increase the power and intensity with that. Remember, power and intensity can be an issue for safety. So if the question gives us an option to improve the quality and offers you to increase the power or intensity, that's usually the wrong answer. We should avoid increasing intensity or power because that can cause some damage to tissue. And the last two things we mentioned, the speed and the wavelength, and the propagation speed is a factor, or as is a matter of the medium itself, determined by the stiffness in the same. So it's stiffness, same as the speed, so they are directly related to each other. And we mentioned the more the body or the medium is dense, more mass in that volume, then it will resist more, so the speed will be lower. Now, the equation that we need to remember for the exam is propagation speed equals frequency times the wavelength. And for our purposes in the exam, usually the speed will be 1540 meter per second. And it's the same as 1.54 millimeter per microsecond. So if the question gives you frequency in hertz, you will use this one because it uses the per microsecond. If it gives you the question in hertz frequency, you can use the 1540 meter per second. And again, since the wavelength here is related somehow to the frequency and the propagation speed, the way we change wavelength is either changing the medium or changing the source. But sonographer cannot change the wavelength because we cannot change the frequency or the medium just by turning something. We have to change the whole medium or the whole probe. Okay, so that's the end of today. We're gonna do some few questions to summarize and review these topics quickly together. So let's do some questions together. So the first question is, the speed of sound wave in tissues is, and the answer is 1540 meter per second. And for, again, the purposes of the exam, we need to remember the other unit, which is 1.54 millimeter per microsecond. Okay. The relationship between propagation speed, frequency, and wavelength is given by the formula. It's propagation speed equals frequency time wavelength. And again, the units, very important. I keep mentioning the units because that's the way they will give you the same answers, but different units. So we need to know which number we use or which unit we use. The next question is, what is influenced by medium through which sound travels? And we mentioned here that there are different ways that the medium can affect. All of us know that the medium will affect the speed, but also through that equation, which is speed equals frequency times wavelength. If we change the speed, that will affect the wavelength, then the answer will be wavelength and speed. Now, if amplitude is doubled, then intensity is, so before we think about the question, we write the equation. So again, power equals amplitude square, intensity equals power divided by area, which equals amplitude squared divided by area. Area here is fixed. So if you increase the amplitude twice, then the intensity will go up 4 times. So the answer is, it will quadruple. Sound travels faster in a medium with which of the following characteristic? As we said, the medium determines the propagation speed through 2 things. We mentioned the speed is related to the stiffness, and we said stiffness and speed, they are the same, so it's direct relationship. And we mentioned that propagation speed is inversely related to density. The higher or the more dense means more resistance, and the speed will be lower. So the sound will be faster in a medium with a higher stiffness, okay, and with a lower density. And the answer will be B, low density, high stiffness. Period is a measure of duration of one wavelength. As we mentioned here, this is the timeline. So this is time, unit of like microsecond, can be second and what so. So this is one cycle. The duration of that one cycle over time is one period. We remember that frequency times period equals 1, and that's very important. If both power and area are doubled, then intensity is, so we apply the same equation. We said intensity equals power divided by area. So if we increase the power, we double it, and I'm sorry. We're gonna write the equation again. If the power and area are doubled, the intensity. So we said intensity equals power divided by area. So if we increase the power here twice and the area twice, then there should be no change. So the answer is unchanged. I think that's it for today. Thank you so much for joining me. I will be discussing in the next section the pulsed ultrasound. We're going to talk about basic rules and what is the pulse in the next section. I'll see you then. Thank you so much.